Welcome to Study Loop.
So we need to find the instantaneous rate of angular acceleration at t equals 3 seconds, and then find the average angular acceleration from 0 seconds to 3 seconds, and then comment on why it might not be the same. So first, omega zt, let's write this function, is going to be equal to gamma minus beta t squared, where gamma equals 5 radians per second, and beta equals 0.800 radians per second cubed. At this point, we know that for A, alpha z of t is going to be equal to the derivative of omega z of t with respect to time. So this will be negative 2 beta t, or negative 1.600 radians per second cubed times t. Alpha z at t equals 3 seconds will simply be negative 1.6 times 3, or negative 4.800 radians per second squared. Omega z at t equals 0 seconds is going to be simply gamma, or 5 radians per second. And then omega z at t equals 3 seconds is going to be equal to 5 minus 0.8 times 3, or 3 squared rather. And this will be equal to negative 2.200 radians per second. To find alpha z average, you just take these two values divided by time. So it would be negative 2.2 minus 5 divided by 3. And this is going to be negative 2.40 radians per second. So this would be your first answer. This would be your second answer. This would be your first answer. And this would be the general formula for the angular acceleration. Now it's asking, why aren't these the same? So why is the instantaneous angular acceleration at t equals 3 seconds not equal to the average angular acceleration over these 3 seconds? And this is because this right here is not modeled by a linear function. So if this is not modeled by a linear function, that means that the average angular acceleration is going to vary with time. So because the angular velocity is not modeled by a linear function, the average angular acceleration is not equal to the instantaneous angular acceleration at t equals 3 seconds. Again, that slope, or the slope of the angular velocity graph, or the angular acceleration, is not going to be constant. It's not modeled by a linear function. So again, those averages are going to be different than the instantaneous angular accelerations that are found. And that's the end of the solution. Thank you for watching.